VLSos here. This is a video lesson on differential solutions. So we're going to start with the differential equation. We're going to make a table of information and graph to make a slope field. But we'll also use extra information in order to find a particular solution within that slope field. First, let's take a look at a differential equation. dx over dy is equal to negative x over 10 plus 2y over 10. We're going to graph this differential, which will produce a slope field. We're going to do that by choosing values for x and values for y, and then using the equation to calculate the derivative at those locations. I'm going to choose y to be 1 and show how the derivative is affected by the change in y. To start off. With my given choices, x is going to be 1 each time, and y will start at negative 3. So I'm going to have a negative 1/10 plus a negative 6/10 to make a total of negative 7/10. When y is equal to 1 and y is equal to negative 2 and x is still 1, then I still have the negative 1/10, then I'm going to be adding negative 4/10. And if I catch on to this pattern, as y increases, the derivative is going to increase by 2/10 each time. So that can speed up the values in the table. Let's plot these derivatives. So what I'm plotting is a column where x is equal to 1 each time. The y value of negative 3 is where we're going to start, and we have a slope of negative 7/10. So it's not quite a slope of negative 1, but we're going to estimate that with a tiny tangent line that has approximately negative 7/10 slope. When we have a y value of positive 3, then the location is here, and the slope is going to be a positive 5/10. That's a slope of 1/2, which will approximate like that. In between, the slopes are going to, as I increase y, the slopes are gradually going to increase. I have a horizontal in between 0 and negative 1. So with a y value of 1/2 is where I'll have a 0 tangent, slope of tangent. Following these patterns very roughly, I can fill in how the tangent line slopes must change gradually between those locations. Let's get a sense of how it's changing horizontally. So I'm going to add to my table a new column for x, a new column for y, and then the derivative using the equation at that location. And this time I'm going to fix y to be 1 and change x from negative 3 to positive 3 to see how the derivative changes horizontally dependent on x. So I'm going to be finding the slopes along all these points where y is equal to 1. If we put negative 3 in for x, we're going to have negative 3 or positive 3/10 plus 2/10 to make 5/10. When x changes to -2, it'll be -2 or positive 2/10 and 2/10, which is 4/10. And if x increases by 1 each time, I can see the trend in the derivative is going to go down by 1/10 each time, which will help me quickly fill in the table of values. The zero derivative is located at 2, 1. On my graph, 2, 1 is where we have a zero derivative. To the right, when x is increasing, that derivative is going down slightly. And to the left, the derivative will be increasing by 1/10 each time, which will be shown by an ever so slightly increase in the derivative as we go to the left. So we have two trends to follow. As we go right, we decrease the derivative slightly. As we go left, we increase slightly. As we go up, we increase, and as we go down, we decrease. Now, upward movements and downward movements change more rapidly. When we go up, we increase by 2/10, but when we go left, we only increase by 1/10. With these patterns in mind, I can complete the sketch of the slope field. It's best to do at zero derivatives, so I go up, increasing gradually, and going down, gradual decrease. The zero derivatives are going to follow along an oblique. And we can get to the point where we have enough to begin to visualize how the function y, for which this is a graph of the change of, can follow a trend. This derivative, this differential equation is sophisticated enough that depending on where we are in the graph, the trend following these derivatives is going to be different. So we could be given some more information to work with, as we often do in contextual problems that involve differential equations. We could say, graph the y with the derivative or the slope field given coordinates or values for x and y. And in this case, to practice, when x and y is equal to the point 0, 1, that means that we're going to graph the function that is going to go through this point 0, 1. So we have the slope field to give us the trend or general shape of this function. So if the function y is going to go through this point and follow the trends of this derivative, is very generally going to look something like this. And again, we can make a sketch if for every point on this line, then the derivatives are generalizing the rate of change at those locations. To be given the point xy of 0, 1 means that our line has to pass through that location, because that location is then guaranteed to be on that line. And look what happens when we're given a different point. If we're told that the line or the specific y graph that we're going to graph goes through a different point, such as 4, -1, then that means that we want to see what a line that passes through this location would look like. It's going to follow a very different general trend, and it might look something like this. Differential equations can be very sophisticated. A slope field can give the human eye a general idea of what any particular solution might look like. And a particular solution requires more information than just the differential equation, which tells us how all potential solutions change. And often that information comes in the form of a specific x and y value that then that specific solution must pass through as it follows the general change that the slope field is depicting.